35th Jansky Lecture. The Jansky Lectureship was established by Associated Universities, Inc. to recognize individuals who have made outstanding contributions to astronomy. It is named for Carl G. Jansky, who discovered cosmic radio waves in 1933. It's a special pleasure to recognize Carl's son David and his nephew Curtis, who are with us tonight. This year, the Jansky lecturer is Professor V. Radhakrishnan of the Raman Institute in Bangalore, India, where until recently he was the director. During his career, he has worked in the United States at Caltech, in Australia, Sweden, and the Netherlands. Among his many honors, he is a Fellow of the Indian Academy of Sciences, a Foreign Fellow of the Royal Swedish Academy of Sciences, and a Foreign Associate of the United States National Academy of Sciences. He has an honorary degree from the University of Amsterdam. Professor Radhakrishnan is best known for his research into the polarization of cosmic radio waves using interferometers. This work first led to the discovery of the Jovian radiation belts and later to an understanding of the polarization properties of extragalactic radio sources. His interpretation of the polarization observations of pulsars provided convincing evidence that they are rotating magnetized neutron stars. Rad, as he is known to his friends and colleagues, is a longtime friend of the NRAO. About 35 years ago, I tried to hire him, but he chose instead to sail from England to Australia in a 35-foot trimaran with a few friends. It's a pleasure to have you back here tonight to speak on the topic, Astronomy's Devices. Please welcome Professor Radhakrishnan.
Good evening, ladies and gentlemen. Is it on? Starting from antiquity and exploding in the post-World War II period, discoveries in astronomy have revealed a whole gallery of objects and phenomena that could hardly have been imagined or foreseen before they were found. Any news from above always seems to make good press. And so there is also considerable public awareness of many of the spectacular discoveries in astronomy and of the people who made them. Earlier Jansky lecturers who have been fortunate enough to make such discoveries have chosen appropriately to talk about them. For this evening, I have chosen a topic inspired by the man after whom the lecture is named, and that surprisingly has not been chosen before. I have in mind the devices often made or intended for other purposes, but which, when turned skyward, have revealed to us the wonders that popular lectures and TV programs are about. For me, they are the unsung heroes that have made these discoveries possible. The exercise. As a supreme example of the devices I wish to talk about, I'm going to start with one made by nature herself, which was the only device used in astronomy for thousands of years, the human eye. Apart from sticks and stones stuck in the ground to sight alone, it was the naked eye that followed the motions of the sun and moon against the background and predicted their eclipses to astonishing accuracy. It observed thousands of stars that twinkled, a phenomenon that one came to understand only relatively recently as caused by turbulence in the sea of air above us, an effect that continues to plague ground-based observations. Against the fixed background of the stars was the wandering of the planets, whose study led to our knowledge of the solar system, and from it, the theory of universal gravitation. Among the transients that were naked eye discoveries were the comets that put on such a spectacular show, often returning to more encores. The sporadic brightening of the stars that we call novae, and of course these supernovae. The eye, a tiny marvel, is it bright enough or you want to reduce it to 8? With an opening less than a centimeter in size, is a truly superb detector with a resolution of 100th of a degree and a sensitivity that allows you to find your way at night by the light of stars alone, a feat unmatched until recently. If you brag to your friends about the number of pixels in your latest digital camera, let me tell you that the eye has 100 million receptors, whose function, incidentally, of the retina was first explained by an astronomer, Kepler himself. If you're impressed with your fancy camcorder that takes the shaking of your hand out of the picture, think of what the eye must be doing to keep the ground where it is when you're walking about and shaking your head and rolling your eyes. There is so much of the brain in the eye doing what is called signal processing in the jargon. 1 million nerve fibers take away the information from about 100 million receptors, so you have what you call compression. It takes just about the minimum physically possible amount of light to trigger the eye. And I find it amazing that anyone with good vision can actually discern an object 1 million light years away. That's the distance to Andromeda, our sister galaxy, which looks, we believe, as our Milky Way system would if we were to see it from there. But as with all human faculties, age and illness take their toll with our vision. And already many hundreds of years ago, spectacles were invented to help people whom you will soon call visually challenged. Bits of glass were ground to bulge both inwards and outwards to compensate for both near and farsightedness. And it was, if you like, shows a spectacle peddler who has to go around with a whole set of glasses because people had to try them. There's no way in which you didn't have computer eye testers in those days. And the story is that it was the act of a spectacle maker who did some experiments by putting two lenses, one convex and one concave, in the ends of a tube and looking through them. And another story says it was the kids who were playing who actually noticed that, in fact, you could get magnification. But the point was it resulted in the invention of the telescope, the next and among the greatest of astronomical devices. It was considered for use in early warning of enemy ships approaching one's harbor, but it took the genius of Galileo to first point it upwards and recognize celestial evidence of the universality of physical laws. The cratered surface of the moon had shadows exactly as we have shadows on Earth. Jupiter had moons that went round it just as our moon goes round our planet. Much more difficult to observe was that Venus had phases like the moon, which was dramatic evidence that it went round the sun and not the Earth. With the telescopes that you see in the picture, Galileo accumulated sufficient evidence in 8 months to demonstrate that the book of Genesis, the philosopher Aristotle, the astronomer Ptolemy, and the theologian St. Thomas Aquinas were all up the creek. He shouted his findings from the rooftops and, as we all know, got himself into serious trouble, including house arrest for life. The brightest side, if you could call it that, was that he didn't get burnt like Bruno. High magnification requires a large separation between the lenses at the two ends of a telescope, resulting in a long and unwieldy object to handle. I have an example to show you how crazy this got in those days. The telescope you see there was 150 feet long. Attempts to shorten it by having fatter lenses produced impossibly blurry images for reasons not understood at the time. And for a century and a half, astronomical telescopes were long and lean and lousy. Newton was born in the year Galileo died. among his many discoveries was that sunlight, if passed through a wedge-shaped piece of glass called a prism, would split up into the colors of the rainbow. The connection with telescopes is that lenses are in fact prisms, and so they suffered naturally from what the professionals call chromatic aberration, which is just a way of saying that when things are finely focused, the image doesn't look white and proper, but is colored. And so Newton invented a new kind of telescope. This is not a very good picture, but at least you can see what you have here is a reflector and not a refractor. Light comes in from there and then gets focused and then goes out there. The point about this telescope was that this curved surface which did what the lens did, does it now identically for all colors. Now, although this concept is used in every contemporary major astronomical telescopes, its motivations, might surprise you, were totally erroneous. You could read through all of that, but I can sum it up by saying that Newton believed and explicitly stated that the bending of light and its separation into its constituent colors had to go together. He thought dispersion and deviation were linked together intimately, and that you can't have one without the other. Mistakes, erroneous or stupid statements like that by great men never really stop the progress of science, but they can delay developments. And what happened in this case was that the emergence of combinations of lenses made with different kinds of glass like crown and flint were delayed by years and years. These things were called achromats, and when they finally came, they took over, and for I think over 100 years or so, all the telescopes used refracting lenses because metal reflectors like Newton's were very poor mirrors, and silvered glass was 200 years into the future. A different and all-important property of a telescope for astronomy is its ability to gather more light from a distant object than the human eye by having a lens or a reflector much larger than the size of the pupils of our eyes. The ability of a pair of binoculars to illustrate this aspect seems surprisingly to be less well known than its ability to magnify, which everybody who's looked through a pair of binoculars is conscious of. I suggest that for those of you who don't know this, try looking at a distant tree or bush at night with large diameter binoculars, not opera glasses, and I think you'll be startled to see the leaves as if it was not so dark. Just seeing astronomical objects was one thing, but what made astronomy an exact science was the ability to fix their positions in the frame that appeared to go around the Earth as it spun around. This translated very simply into measuring the precise instant of time at which the stars transited a north-south line on the sky called the meridian, and it required two inventions. The first inspired by an insect in the year 1604. A spider made a fundamental contribution to positional astronomy by spinning its web within a telescope at the focus of the objective lens exactly where the image of the star or planet was formed, and was magnified by the eyepiece in the same way as the image. This led immediately to the invention of the crosshair, or replacement of the spider web by a pair of whatever it is, which suddenly enabled accurate measurements, as it defined precisely for the very first time the direction in which the optical telescope was pointed. The other invention, you not only need to see the star, but you also need to know what time it is, was the pendulum clock invented by the great Dutch scientist Christian Huygens. And this vastly improved the standard and accuracy of astronomical measurements. For over 200 years, the function of the astronomical telescope was to collect light from different directions in the sky and squeeze the pencil down to a size small enough to enter the human eye, which was the only detector available. Such observations were made with telescopes ranging in size from less than a meter to over 10 meters. So you're wondering what I'm saying. And this was the period when telescopes were described by their length and not their diameters. Let me show you a telescope invented again by Christian Huygens. This was only about, I think, 40 feet or 30 feet or something like that. But he had this very clever arrangement, which you can see up there. He had a string so that when you pull this tight, it automatically aligned the objective and made it parallel to the eyepiece which he had. But let's not laugh at this. Observations with such telescopes led to the discovery of new planets, satellites of planets, double stars, clusters of stars, nebulae, and impressive lists of stars. One famous catalogue listed 1/3 of a million stars observed with an instrument 3.5 inches in diameter. But the eye, sensitive though it was, lacked the ability to add new information to old beyond the duration of 1/10 of a second or so, which is the persistence of vision. So the next revolution that was needed to look deeper was the ability to accumulate a weak signal over a stretch of time. And the process that would do this originated from the inspired but empirical meddling of a scenery designer and artist looking for a way to record the forms and perspectives of nature for the design of dioramas. I don't know how many of you know what a diorama is. What it is a painting without borders, depicting, it's usually in a room which is all closed, and then it's illuminated in a way to give an illusion of reality. This one shows the flight of the Holy Family to Egypt, which I thought might be an appropriate one for a Christian country. It was invented by Daguerre in Paris, who is also credited with the invention or discovery of photography some years later in 1839. You may have heard of daguerreotypes, which is the name given to these photographs, which were made at that time. They were made by a process involving plates of silver, trays of iodine and mercury, slow heating in the dark, more than reminiscent of alchemy, made by a process which is totally unknown, but which worked and immortalized him. Quite strangely, there you see the earliest daguerreotype, and this is one of himself. For totally unconnected reasons, a well-known astronomer was also part of the story of the development of photography. John Herschel in England, when he heard of Daguerre's success, immediately produced a photograph, and it turned out to be a photograph of his famous father's famous 40-foot telescope, which is now the icon of the Royal Astronomical Society. That's a picture that you see there. And this is the one made by John Herschel in 1839. That's John Herschel looking like a mad scientist. And his friend was a guy called Fox Talbot, who was a genius, a polymath, Egyptologist. And he had invented a negative-positive process, which is the kind that we use in astronomy today, and hadn't bothered patenting it or making a noise about it. Somebody described it as saying he was British, so being first was beneath him. So anyway, he was a friend of John Herschel's, so this picture was produced. Now, what happened was that 20 years earlier, John Herschel had discovered, something in chemistry, that the normally extremely insoluble salts of silver could be dissolved easily in sodium thiosulfate, or hypo as we call it. This discovery, which was totally useless at the time, when applied to the very temporary and unstable daguerreotype, and also to the Fox-Talbot negative-positive system, suddenly made photography practical. An astronomer, by inventing a photographic fixer, had made permanent image recording possible. Some 40 years or so later, the dry gelatin plate was invented, and that was the first time you could have long exposures. It was possible to make long exposures. And it was in 1883 that a 30-minute exposure of the Orion Nebula, made with a home-built telescope by an engineer famous for constructing the London sewerage system, showed stars too faint to be seen by eye using the same telescope. Ainsley Common had transformed photography from a mere recorder of a visible scene to a detector of the unseen, and was most appropriately given the gold medal of the Royal Astronomical Society in recognition. My comment is, long live amateurs. 100 years later, astrophotography was taken to its peak by David Malan of the Anglo-Australian Observatory, both to make important discoveries and also to popularize astronomy. I'm sure you've all seen pictures of his and calendars. But I had this picture here because it is of the same object as the one taken by Ainsley Common. There was no looking back, and photography rapidly replaced the eye as the only detector. It did so not just for images, but equally importantly for capturing the information buried in the spreading of the wavelengths of light. We saw earlier there that Newton had separated the apparently white light from our nearest star, the sun, into a range of colors called a spectrum. A century later, the German physicist Fraunhofer placed a narrow slit before the prism and invented the spectroscope or spectrograph, the next great astronomical device. Suddenly it was seen that Newton's spectrum of light was not smooth, but in fact penetrated by a series of narrow lines that came to be named after Fraunhofer. The next breakthrough was the recognition around 1860 by two other German physicists, Bunsen, known for his burner, and Kirchhoff, known for many, many other things, that these dark lines were due to absorption by colder atoms in the sun's outer layers of hotter radiation, in all these lines that you see here, from inner regions. By visual inspection, they identified the elements sodium and iron in the sun, showing, I can't help quoting Virginia Trimble, that stars were made of people stuff. More significantly, they ushered in astronomical spectroscopy, the way to detect what was out there, sometimes even before we knew it was here. Helium was first discovered in the solar spectrum and named appropriately after Helios, the sun, before it was found on Earth, and much longer before it would play a crucial role in devices that would enable major astronomical discoveries. There was also now the possibility of determining the motion of distant matter through the Doppler effect, popularly described as the change in the tone of the whistle of a train approaching and then receding from the listener. To achieve this would require a means to detect the position of lines, such as those you saw in the previous picture, so weak that one would need long exposures and accumulation of the signal. And this was just what photography could do for spectra, as it did for images. In fact, it became such a powerful tool for studying stars that the Astrophysical Journal was actually founded with a subtitle. I don't know how many of you have ever seen this or known this. It was called an International Review of Spectroscopy and Astronomical Physics. And I had to do some research to find out that this was the last issue which actually carried that subtitle. Chandra had an editorial which said that he's changing the number of issues per year, but he slowly sneaked the subtitle out of the way without making any mention of it. The demands of photography and spectroscopy now governed telescope design, culminating in the 60 and 100-foot telescopes on Mount Wilson in the early 1900s. From these flowed discoveries as momentous as that the Milky Way was just one galaxy among many, and that they were all going away from each other with a speed proportional to their separation, the expanding universe. Both astrophysics and cosmology were made possible by something invented to make dioramas. Astronomical spectroscopy had revealed so much by just looking in little windows within the 1 octave from red to violet that our eyes are sensitive to, that it should have been obvious to any intelligent person that whole new views of the universe were waiting to be discovered in the vast expanse of the electromagnetic spectrum if only we would look. But it didn't happen that way. Bell Labs wanted to improve radio communications, and they put a young engineer called Jansky, whom they had hired, on the job of studying the so-called static that was the cause of the interference. They wanted to know what it was. Nobody in his senses could have imagined that this structure of wood and poles and wheels and wire would bring us news from thousands of light years away. It's a tribute to Jansky's superior quality as a scientist that although he found what the company had asked him to find, he persisted in accounting for something very weak that was left over and made a historic discovery at the age of 26. Radio astronomy was born, and there were now decades and decades of radio spectrum just waiting to be explored as and when the right devices and people got together. And World War II, for all its ills, provided just such a golden opportunity. The desperate need for effective radar, both ground-based and airborne, led to intensive development by physicists on both sides of the Atlantic of devices that would operate in different regions of the radio spectrum, making possible, among other things, the microwave oven that you have at home. Radar equipment and expertise in operating them led after the war to several groups in different countries doing what Galileo did, away from approaching enemy craft up at the sky. England and Australia were the leaders in the field, but in several places in Europe, like Holland and France and even Sweden, where I worked for a while, one used the so-called giant Würzburg radar antennas, which the Germans had installed all along the coast from Spain, I think, all the way up to Norway. Many of these were moved from the coast where they had been installed to radio observatories. That's a new post-war phenomenon. The name didn't exist before. I heard a story about this particular telescope that when they removed it, they found on the instrument panel some markings. Apparently these were the equivalent of notches that Wild West gunmen used to put on the whatever it is, which marked the number of Allied planes shot down because of the radar used at this particular telescope. Radio astronomy revealed innumerable sources dotted all over the sky. But the defining moment, in my view, was when the first Jansky lecturer, John Bolton and his collaborators in Australia, using antennas like our familiar TV ones, detected and identified two strong radio sources with faraway galaxies. Radio signals were revealing a different and distant universe. And when sometime later, the second brightest radio source in the sky was identified with what the biggest optical telescope available then, that's the Palomar 200-inch, showed as a faint little smudge, I think everybody understood that the weak radio sources must be billions of light years away. This raised the question, in some minds, how come radio sees farther than optical? Why can't optical telescopes, if big enough, see past the faint radio sources that we now see in untold numbers? Both questions were answered in a very strange but decisive way by the next major astronomical discovery made at Bell Labs 35 years after the first one. The device used was a 20-foot horn reflector designed for very low noise communications. The special thing about the design was that it's insensitive to stray radiation from unwanted directions. These days it's called an unblocked aperture and is the principle that is used for the Greenbank telescope, which has just been completed. More than one aspect of the second discovery was like a replay of the Jansky story. All known things accounted for, except a little annoying left over to explain. It wasn't annoying, mind you. Once it was appreciated that the leftover wasn't due to what the pigeons had dropped in the antenna, but from the Big Bang. According to cosmologists, the radiation that was detected comes to us from a time long before galaxies and stars were formed. And if that's true, there was nothing beyond for optical telescopes to see, no matter how big they are. 2 more Jansky lecturers for NRAO, 2 more Nobel Prize winners for Bell Labs, but no let-up in the pressure to improve telephone services. As an aside to the astronomers in the audience, who may actually be the majority today, may I just say that I've always been struck by the coincidence that this vital contribution in support of the Big Bang theory depended crucially on the use of helium, whose observed abundance in the universe was another prediction of the same theory. The world's then most sensitive receiver, which was housed in the cabin over there, called a maser, required cooling with liquid helium to achieve its performance. I have much more to say about Bell Labs and their devices, but wish now to digress and say something about waves and particles. Light brings us news of the universe, said the great William Bragg early last century. We've just seen that news of the universe is also brought to us by radio waves. Thanks to the genius of Maxwell, who unified electricity and magnetism, we think of both kinds of messages as just electromagnetic radiation, and differing only in the length of the waves. For light, this is of the order of 1,000th of a millimeter. For the waves that Jansky detected, it was 15 meters, and most radio astronomy being done today is at wavelengths which are in between. The prime motivation for Newton's invention of the reflecting telescope was to make it achromatic over the spread of wavelengths that the eye responds to a mere 2-to-1 ratio. At that time, even the ultraviolet and the infrared weren't recognized as channels that might be bringing us interesting news from the sky. And radio was a few hundred years in the future. Grote Reber, who single-handedly carried Jansky's torch through the war years, he understood the principle that a reflector like that was achromatic. And he made the first parabolic radio telescope, which he used at several different wavelengths. But a telling illustration of the soundness of Newton's concept is that a finely figured, large metallized mirror is perfectly achromatic, not just over a 2-to-1 ratio, but a factor of 100 million to 1, all the way from the near ultraviolet through the radio spectrum. As long as the surface is smooth and the wavelength is smaller than the dimension of the reflector, it will be a perfect collector of any radiation that falls on its surface. The biggest modern optical telescopes today are the Kecks, each bigger than Reber's and capable of doing superbly anything that Reber's antenna could do. I know you're going to remind me that they cost a little more. It's like $100 million each. But the point I'm trying to explain, a very important point, is that when you change wavelengths by, let's say, a factor of 1 million on one of these, it's not the telescope but what you put at the focus that needs to be changed and understood. The functions required at that of receiving the messages and storing the information for later analysis. Yeah, they're both of them roughly the same size. Moses must have appreciated the importance of this aspect when he lugged all that heavy recording gear up the mountain. For operation at light wavelengths, we've already discussed 2 kinds of devices that can be used. We could put a human eye at the focus and use our memory to draw pictures like people did of canals on Mars and so on. Or a photographic plate which would be more sensitive, more faithful, and more permanent in its memory. But in both these cases, whether you use the human eye or whether you have a photographic plate, the process of detection belongs to photochemistry and involves a different aspect of radiation that we can no longer ignore. When electromagnetic radiation goes from one place to the other, it behaves like a wave. Phenomena like refraction, reflection, diffraction, interference are all wave properties and basic to the design of both the telescopes in this picture. But there's a Jekyll and Hyde behavior when it comes to radiation giving up its energy. Einstein got his Nobel Prize not for relativity, but for showing that the energy of radiation arrives only in packets called photons, no matter how weak the radiation. The best analogy I could think of is that of a dripping faucet, where you get drop, 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 and then you're annoyed, so you go and tighten it. And all that happens is that the interval between the drops increases, but when you get water, it's still a drop, you see. Photochemical detectors like the eye and photographic emulsions need photons with a certain minimum energy to activate them. They are thus color sensitive, and radiation of wavelength longer than a certain limit cannot initiate the required chemical changes. This is why you use a red light in a photographic darkroom. It doesn't affect the emulsion. This is just as in Einstein's effect, where electrons, I should have had that before, I'm sorry. Yeah. This is just as in Einstein's effect, when electrons are emitted from the surface of some metals only if the wavelength of the radiation is shorter than a certain limit. And that's in the next one here, where the electrons that are emitted can be accelerated by batteries to operate a recording instrument. This is light falling on a metal. Individual radio photons, for the reason that you saw on the previous slide, have 1,000,000 times less energy. And even in swarms of millions, cannot free an electron from its atom to be accelerated and used further. Astronomical radio sources create currents and antennas too weak to trigger any detector unless they can be amplified, strengthened, boosted, or whatever it is, something to make them more powerful. One such device was invented by Leader Forrest in 1906 and was called a triode. And the important point is that the electrons needed to do the job were liberated not by light, as in the photoelectric effect, but by heating a filament in an evacuated tube. The stream of electrons, which go from there to there, can then be modulated by the weak signal from the telescope. It's not a very good artistic drawing, but that's supposed to be a telescope. And then the amplified signal will operate a detector. Now, I was talking to someone earlier today. So anyway, I used to think that only those well past retirement would have seen a vacuum tube, leave alone used one to make anything. Imagine my surprise when I discovered quite recently that the amplifiers used in rock bands have tubes like the 6L6 and 6V6 that some old fogies here might remember, because other types of amplifiers cannot sound right. This is my kid who plays the bass guitar and is a bit too big for me to tangle with. I quote from an ad for such amplifiers: "Only vacuum tubes achieve warmer, more attractive sound and cooler, smoother transitions," end quote. In any case, here's a picture from my collection of over half a century ago for the benefit of those who don't know what vacuum tubes are about. This is a magnetron, and these are klystrons, and those are acorn tubes. Those are transmitting tubes of the kind that radio hams would use. And this is a special tube. It's a lighthouse tube, which was the only thing that could be used to generate the local oscillator for a 21 centimeter receiver in the 50s. Anyway, I come now to an important point. it was not the type or size or frequency of Jansky's antenna that was crucial for his brilliant and historic discovery, but the device that built up the signals to a detectable level. The radio universe was made apparent by the vacuum tube amplifier. The lightest of the particles of which all matter is made up is my friend the electron, mankind's greatest servant. Evaporating it with heat from a metal in a vacuum enclosure and accelerating it with electric fields ushered in both the name and the age of electronics. The triode was not invented at Bell Labs, but they lost no time in buying up the patent. Improving its performance and using it for long-distance telephone communications. For wanting something more reliable, less bulky, and less heat-producing, they launched an unrelenting effort to invent other and better devices to amplify signals, which goes on to this day. The first was the traveling wave amplifier, a different kind of vacuum tube with an electron gun, a long helix along which the signals traveled and grew in strength. Although it played an important part in transcontinental communications for a long time, it made only a brief appearance in radio astronomy in the 50s, which I shall not dwell upon. The next major device was the maser, which I've mentioned already. This is not really a maser, this is a model which I made. I've mentioned this receiver in connection with the detection of the microwave background radiation. What's special here is that unlike the free electron devices, which required heating to several hundred degrees above ambient, the maser required cooling to within a few degrees of absolute zero. I think in American that's 450 below. The signal interacted with the crystal of ruby and was amplified by the energy given to the ruby at another frequency and not DC from a battery, as with all devices which used free electrons. The price paid for this superior performance was a heavy, complicated, and cumbersome device, despite which for some years there were many radio observatories that had a maser receiver. I spent a year at 1961 at Bell Labs, building a couple of them for Caltech, during which time I think I learned more than in any other year of my life. An almost concurrent development at Bell Labs was the parametric amplifier. Like the maser, the device was a solid, and the energy to amplify the input signal was again some other frequency and not also called a pump and not a battery. But look, suddenly it was minute. It was 4.5 millimeters, and so that's even less. It could be used even at room temperature, and for over a decade, the parametric amplifier served as the front end of choice for radio astronomy receivers in many observatories. It's now been totally displaced by the transistor, another device invented by our friendly telephone company. The history, as many of you may know, was that Bell Labs assembled a bunch of super whiz kids towards the end of the war to find a replacement for the vacuum tube as a repeater in long-distance telephone communications. They did, and created a revolution beyond imagination. They found a way to remember, it's always electrons that do the work, but they found a way to manipulate electrons inside a solid and at room temperature. This suddenly made, in principle, integrated circuits and microelectronics possible. But it took 2 decades and other inventors to actually, for the promise to be fully realized. 3 more Nobel laureates for Bell, but no big deal when you think of the change wrought to the whole world by their invention. The particular type of transistor called a FET, now used as the most sensitive amplifier over the whole radio spectrum, is the kind that functions most like a vacuum tube, and so something that I have least trouble understanding. It was invented in theory by Bill Shockley, whose picture you see over there, the brilliant leader of the group that Bell put together, when they started their work in the late 40s. By the time this was realized in practice, Shockley's associates had left him as absolutely impossible to work with. The public hated him because he wanted scientific investigations into the possible dependence of intelligence on race. He died without getting adequate credit or the financial benefit for thinking up the greatest invention of the century and starting Silicon Valley. His was the first company. The ability to pack the equivalent of many million vacuum tubes into a tiny chip has transformed every branch of human activity. The consequent change in size, speed, and sensitivity of radio astronomy receivers is, in my view, just a minor, inconsequential byproduct of this major revolution that is continuing to change the world. It's very significant that both the physics and chemistry Nobel Prizes for this year were awarded to scientists who developed devices. The only vacuum tubes that are still made in the millions are for people to stare at dumbly. You are expected to do this all day at work, whatever your profession. But if you want a break, you can go home and then you can watch TV. If I can go back to my hang-up about the dual aspect of radiation, then anything shorter in wavelength than visible light, like ultraviolet, X-rays, and so on, arrives in packets with more than enough energy to rip electrons off atoms and die in the process. So none of this radiation can actually get through the atmosphere and reach the ground for that reason. And so we remained in total ignorance of whole new views of the universe waiting to be seen at higher and higher energies. It's World War II rockets, like this one here, and high-altitude balloons carrying detectors that gave us our first glimpses of totally different scenes from those we knew from lower frequencies or longer wavelengths. But it was the launch of Sputnik and the ensuing politically motivated space race that made possible bigger and bigger artificial Earth satellites that are bringing us a continuous stream of new and sensational astronomical discoveries. Most of these are in windows of the electromagnetic spectrum inaccessible from the ground for the reason I just said, that the radiation can't get here. But the Hubble Space Telescope is making equally sensational discoveries in the visible range in spite of its small size by ground-based standards. The advantage which makes this possible is not getting closer to the object, but being above the atmosphere and not suffering from the kind of twinkling that I mentioned earlier. So I was just saying, X-ray photons have more than enough energy to make their presence felt when they pass through matter. And when it comes to detectors, X-ray astronomers suffer an embarrassment of riches. They have different ways of using the energy of X-ray photons to liberate electrons, to determine the intensity of the radiation. But to know where the radiation comes from would require focusing and imaging as in an optical telescope, something that depends on the wave aspect of the radiation. And perversely, the more energetic a photon, the more macho, so to speak, it gets, and the less it wants its sinuous aspect to be seen or used. X-rays cannot be refracted by any medium, and even the magnificent Keck mirrors cannot reflect them. Its surface would look like a sieve to radiation, whose wavelength is smaller. This is supposed to represent atoms. It's just some picture I took from a magazine. If the wavelength of the radiation is much smaller than the separation between the atoms, I mean, it would go through like a radio telescope with a very large mesh. But tilt the sieve to your line of sight, and then you will get to an angle where the surface looks more or less continuous, like a continuous sheet of conducting material, and you will get good reflection. This is not exactly the physics, but That's roughly the way in which X-ray telescopes work. And here you see a whole series of these cones, all of which are receiving the X radiation at a very small angle and then just deflecting them a little to focus them. As you go up in energy to hard X-rays, the grazing angle that will reflect the radiation gets less and less, and the efficiency of the telescope starts to vanish. There's no way to manipulate the propagation of such very hard radiation. To associate a wave aspect with particles of such high energy is an act of religious faith, and there is no physics experiment which can actually demonstrate the wave nature of very high energy radiation. At even higher energies than X-rays, the impossibility of building any kind of focusing telescope is made up in an interesting way in the behavior of gamma rays themselves. When they pass close to the nucleus of an atom, they sort of ignore the electrons which are around the nucleus of the atom, but they create a pair of new electrons to which they give all of their energy. These two electrons, which you see here, this is a cartoon and that's a real recording. They sort of proceed to blaze slightly diverging trails in a device which is called a spark chamber, and then if you extrapolate this line backwards, then it comes from the direction of the origin of the radiation. There are many sources of such extremely energetic radiation in the sky, and one can make maps showing the position on the sky. I'm just showing you one, and I don't know how you would react to this, but such maps always fascinate me because they're so different from maps of radio or optical sources. Each one of these is just one photon. It's just one piece of radiation. So when you say there is a source over here, all that one has been managed to collect is one single photon. We've already encountered the opposite situation at the other end of the astronomical spectrum, where there's no way of showing the particle aspect of radio radiation. Right in the middle of this enormous stretch, we have light, whose wave nature was demonstrated by Young 200 years ago, and whose particle nature by Einstein about 100 years ago. And what is remarkable is that both aspects of the radiation manifest themselves in the operation of the very first detector that I discussed, which is the human eye. It's the wave aspect of radiation combined with the size of the lens in our eyes that determines the resolution. And the particle aspect, as I already discussed, has to do with the fact that it can create the chemical transformation. I'll now turn to the most modern device which has replaced the human eye in astronomy. We have here a picture of two gentlemen at work in a US lab. No prizes for guessing which lab or which device they were trying to improve. The sound quality of telephones had been good for decades, so what the hell were they trying to do? It's the lack of vision. These gentlemen were creating the picture form so you could see who you were talking to and be seen by him or her. For this, they invented something called a charge-coupled device based on a new principle. Incident light liberated electrons. It's always the electrons that do the work. But the electrons were liberated inside small but separate elements of semiconducting solid, where the charges were accumulated over the exposure time. And then these charges were pushed out one behind the other like a line of boxcars. The contents of each were then used to generate an image with picture elements of brightness proportional to the amount of charge. Now, the energy required to make electrons available for internal conduction is far less than to release them from the solid surface, as in Einstein's photoelectric effect. And so CCDs could work down into the infrared. Higher energies pose no problem, and it's only a question of technical adaptation. The situation today, 30 years after the first invention, is a revolution in the detection of electromagnetic radiation, as spectacular as the transistor revolution which it incorporates. Your electronic cameras, both video and still, the surveillance devices in supermarkets, banks, big apartment complexes, your scanners and innumerable other applications all use CCDs. They are the most sensitive detectors at the back end of every major telescope in the world, and most minor ones as well, at wavelengths infrared and shorter. Apart from imaging, for which they are so obviously suited, they have transformed astronomical spectroscopy exactly as photography did when it was first introduced. Space-based telescopes depend on CCDs and use them well into the X-ray band. One very heartening consequence is that amateur astronomers can put very affordable CCDs on their modest telescopes and do better than the professionals did before they used CCDs too. Now here's a 42-inch telescope and this is a picture taken with this film, which is supposed to be very good, exposure time of 15 minutes in an observatory where there was very little light pollution. There's an amateur telescope, 11 inches in diameter, in a really bad area, same exposure time, and of course you see so many things that you don't see here. I believe that a lot of useful science is being done by optical amateurs today, and I find this some consolation for their sad disappearance from radio astronomy, a field pioneered by radio hams, an ultimate example, of course, being Gros Triber. The emergence of national and international facilities that no single institution or sometimes even nation can afford wiped out the amateur era when individuals who had conceived, constructed, or modified their equipment could feel some justifiable identification with their astronomical findings. I hope I've conveyed my message that astronomy has depended enormously on the use of devices originally created with no thought of the sky in mind. This supports the view of Jared Diamond, a very perceptive social scientist, that invention is the mother of necessity and not the other way around. There are numerous other examples, such as the Global Positioning System, GPS, set up originally for strictly defense purposes, but now used as time and frequency standards at most observatories, and of course, by millions of pilots, sailors, trekkers, rental cars, and so on. Another is optical fiber, which carries the bulk of the world's communications today and is finding specialized applications in astronomy. A very clever use in optical spectroscopy is to use a bundle of fibers, each carrying the light from one of hundreds of stars in the field of view, and feeding it all into a single spectrograph so that all the spectra are obtained simultaneously. This gives a spectacular increase in speed. Optical fibers are the best way to connect radio telescopes in NRA, as is now being done at NRAO. In the year 61, when I mentioned as when I spent time at Bell Labs, there was a guy in the basement somewhere apparently messing around developing optical fibers to replace telephone cables, and I thought it sounded like science fiction. But in this case, I've done a little more research, and we can go much further back to support the theme of my lecture. A patent for a method of manufacturing optical fibers was taken out in the 1930s with the inventor's comment, and I quote, "In case someone ever finds a use for it," end quote. Whatever type of astronomy we are talking about, the ability and importance of being able to record vast amounts of data at high rates will remain paramount. And the last topic I wish to touch upon in the next 2 or 3 minutes is the revolution in recording ability, a development motivated in total oblivion of any astronomical implications. I was very sorry to miss the dedication of the GBT, but my heart was warmed to see that his first light was received on a chart recorder. A most venerable instrument of the vacuum tube era that I have spent years looking at in vain. One Jansky lecturer described the search through hundreds of paper charts to find little squiggles, but in that case they were eventually worth a Nobel Prize. But there's probably no observatory today where you will see such an instrument in actual everyday use. The reason is very simple. The message from on high arrives today not at 1 bit per second, which is just the right speed for a chart recorder, but millions of billions of times faster. And the reason for that is the existence of the ability to generate, collect, and process such data brought about entirely by the transistor revolution. VLBI was conceived because tape recorders existed, and they did because of the entertainment industry. The staggeringly high recording densities available today, and even more that's promised for tomorrow, is thanks to Sony's developments of tapes and drives for its camcorders, not exactly astronomical applications. I think I have said enough to convince you about the extent to which astronomy has been dependent on the use of devices made for applications that normal people can relate to. This should, I hope, help you to see today's astronomer in proper perspective as more likely just another consumer or passenger riding the technology express, and not the hotshot explorer of the universe as always depicted in the media and often believed by the astronomer.